Good afternoon. Hope everybody's doing well today. We have a pretty exciting day. It's, as I said in my social posts, it's been a long time coming. We've got some interesting stuff to do to add bloom filters to HanoiDB. So I will see if I can pull up here a post from Martin Klutman, and we'll talk about that. It's not the best. Here we go. This is not the best diagram, but we'll be talking about what a bloom filter is and why we care. And then we'll add them. I think I found. I hope I bookmarked it. I found this past week an implementation of bloom filters in Rust, which is really a straightforward one, and I think it looks pretty good. There are some other similar data structures I've seen crates for, and no, I didn't put it there. The one that I found should be pretty straightforward to serialize and deserialize, which is really important because it's nice to have these in memory, but ultimately we want to save them and save them to each tree file that we write, so that we can have them for when we load up that file later, and you know, I think I'm kind of dancing around what they are. So let's talk about that, and I'll go ahead and flip over, and people can filter in, and hopefully you won't miss the explanation. Okay. So this is a diagram that Martin Klutman, if you're not familiar with who he is, he's a professor, he teaches in the UK. He was one of the co-authors of the original Kafka implemented at LinkedIn. And he has a very influential book called Designing Data-Intensive Applications. And he goes into a lot of the guts of what are in databases. And there's he's working on second edition, I guess. And this discussion came up this week, very well timed, unintentionally, with what I had planned to do for the stream anyway. But he's trying to get a diagram of what a bloom filter looks like. So I'll briefly explain what it is and why we care. So it's the name is Bloom, after the creator of this data structure, and filter meaning it's a way to determine, is there a particular key in this set, or in this database file in our case. And the nice thing about bloom filters are they're very fast. So you basically hash the key to a set of bits, and then you compare that hash to the bits that are stored in the bloom filter. It is very space compact. So whereas you would need, you know, if you wanted an exact key set, you would need something that is the total size of the keys, of all the keys in your database. But what we're trying to do here with bloom filters is we want to have a quick check before we actually go to disk to find this thing of whether this is in the file. So how do we actually get compact? Well, bloom filters make the trade-off. So they're fast to insert, they're fast to check, and they are small on storage. Well, okay, so what's the catch? The catch is that the way that they are structured means that it's possible for a hash of two different keys. So here in the diagram, this is a good way to explain it. So you have hash of handbag, and it comes out with three bits to set, 2, 9, and 4. This is a hypothetical hash function. I don't know that he actually computed something for this. And this is also a hypothetical Bloom filter of only 16 bits. Ours will be much bigger. So hash of handbag says set bits 2, 9, and 4. Hash of handoff says set bits 9, 15, and 5. Hash of handheld says set bits 6, 11, and 2. So he's taking nibbles of the hash, the output hash, and using those as bits to set. Okay, so you may already see here the problem. It's not necessarily a problem, it's just a potential weakness of the data structure. That between these two hashes, you have bits in common. So, and between these two hashes, you have bits in common. So there's a possibility that you are looking for a key to exist in the set, and that will determine whether or not you actually go to disk to try to read it, or whether you immediately return, no, it's not here. The trade-off here is that you have collisions between these hashes, so there's a possibility that if enough collisions happen, you could get a false positive. So what do we mean by false positive? That is saying, yes, it's in the set, but then you go to look on disk and it's not actually there. However, this does assert that there are no false negatives. So if you hash, say, handheld, and none of these bits are set, that means it absolutely is not in there, because this combination of bits, all of them have to be set in order for it to say, yes, it's there. But if none of them are set, or only one of them is set, then you can absolutely say, no, this is not here, because we know these are the hashes for that key, right? So no false negatives. So it never will say, no, it's not there, when it might be. But it does have false positives. It might say it's there when it's not. Okay? So that's the concept of a Bloom filter. Obviously, he made a very reductive example here. You would never use a 15 or 16-bit, Bloom filter. You would use something much bigger, because you can see that with 16 bits and only 3 keys, we're getting a lot of collisions already. What I mean when I say collisions is that part of the hash of a key says set the same bit as part of the hash as another key. So there's a lot of statistics and like proven results about what are the optimal sizes of Bloom filters for a particular error rate. So, or false positive rate is a way to think of it. And you can set that false positive rate on some of the implementations of Bloom filters, and you can set how many bits should be hashed out of a key, which determines the size of your filter. So there's a lot of ways to tweak these to fit the size of the set that you want to represent. And I think the nice thing about HanoiDB with this data structure is that the size of the Bloom filter will be proportional, logarithmically proportional, to the size of the number of keys that we have in the set, or in a single file, right? So if we say at the smallest level, which our default is 1024 keys, we can tell the Bloom filter implementation, I want to have 1024 keys, and then it can scale its hashing algorithm, or it's the width of the bit vector, to appropriately be able to handle 1024 keys. Now we would probably say, let's tweak the false positive rate. Gain on the mic is a bit low. Thanks for letting me know. Let me bump it up. Tell me if that's better. How about that? Okay. Cool. Thank you. Runoff. Welcome to the stream. So we want to pick parameters that are associated with the size of the data file that we're going to write, both on the number of keys and the false positive rate. And so we're going to get something that is, probably in Rust it'll be like a vec or an array if it uses generic const. I think the implementation I was looking at the other day uses, const generics on it. And it'll be like an array of U64s. And then the implementation of that will, when it says add this key, it'll hash it to a certain number of bits that need to be set, and then it'll go set those on the array of U64s. Okay, so this is essentially a Bloom filter, what it does. And it may seem like, oh, that's kind of pointless, or it's a waste, but it actually will save you IOPS. And since we're writing a database engine, really a key value store that is ordered, we still benefit from having logarithmic access because of the B tree. But if we can avoid that, if we can make a missing key be order 1 instead of order log n, then we're doing a lot better, right? So that is the point of a Bloom filter. It saves you on IOPS on misses. Okay, so I will paste the link to this post into the stream chat. And it's on Blue Sky, so if you're not on Blue Sky, I'm sorry, but there you go. And okay, so it went to chat. Feel free to look at that. He also has another diagram, which is way more confusing. He simplified it. I like this new version a lot better. Okay, so we're going to go to crates.io, and I think that we're going to find this Bloom filter. I think it was Fast Bloom RS. I believe this was it. I think it was this one, actually. Yeah. Okay, so let's look at the docs for this really quick. Nice thing about this one, it's SIMD accelerated. So if you have a SIMD processor, this is going to make the hashing faster and the lookup faster, which is awesome. Okay, so it uses SIMD accelerated Bloom filter. Its default hasher is SIP hash 1-3 using randomized keys, but you can see to configure it to use any hasher. It's significantly faster. I'm assuming that's because of SIMD. But let's look at how this works. So when you create a Bloom filter, you specify the number of bits you want. It has to be a power of or a multiple of 64, because U64, right? And then you can set the expected items. So we could do something like, we want this, and then this number of bits, and then we'll say the expected items is the size of our level that we're about to write. The other way you can do it is, say, with false positive. And this says this is your false positive rate, which we talked about, which is like, this is the probability of the hashes of two separate keys colliding or completely overlapping, right? And then you can, do some other things. I think this is the one I was looking at. Right, space efficient approximate membership set data structures. Okay, they have a bunch of graphs using SIP hash. You can use XX hash, and this is all okay. So this is XX hash is down here. This is speed, member check speed versus items. Okay, so interestingly, the speed gets better. I don't know about these graphs. Okay, false positive performance. Yeah, this is the one I was looking at the other day. Does not compromise accuracy. So you can see the blue line over here is just the plain fast bloom, and it's kind of hugging the optimal. So as the number of items grows, you can see false positives go up. But if they are actually scalable bloom filters, then we can bring this false positive rate down as we get more items by increasing the size of the filter. Okay, so it offers 4 different block sizes: 64, 128, 256, and 512 bits. 512 is the default. So I'm guessing by blocks, they are meaning... Right, so larger block size generally have slower performance but are more accurate. Right. Bloom filter with 64-bit blocks is very fast, slightly less accurate. So I'm not certain what that means with respect to how the bits are chosen. It may mean that over 512 bits, you have had different hashes for different... Oh, this may be related to how it does comparisons. So using SIMD, let's see, 64, that would be 256 would be, no. 128 is the size of a SIMD register, generally speaking. Anyway, I guess we'll find out some more about this. Okay. Right, many bit positions can be derived through SIMD and SWAR-like operations. Okay, hash composition on two 32-bit halves of original 64-bit. So they're using some kind of 64, so the hash algorithm outputs 64 bits. And then it's probably, like the example, probably taking... Okay, so this means that, you know, the hash is like an index into the the bit vector, right? It's not, here's the bits to set. So I'm guessing this is saying here are two 32-bit bits to set. Results in a lot effectively independent. Okay. So fast bloom. Okay, so this is, he's saying you do 24 different hash functions and you mod 64. Fast uses a sparse hash. Okay, so it's like hash, 4 hashes. Okay, so this is what they're talking about when you're saying how many hashes to make. So this is hash this and hash this, or it with the hash of this and the hash of this. Okay. Okay, so given 64 bits and 24 hashes, a bit has a probability of that to not be set, i.e. 0 after 24 hashes. There's a lot of math here. Shout out to Tom Santero. There's a lot of math. Okay, so the bloom filter obviously can have more than 64 bits of storage. The examples they showed above, 1024. We might want bigger. So let's look at the actual API of this. So here's bloom filter. And so we can say with false positive, memory size of the underlying bit vector is dependent on the false positive rate and the expected number of items. So that's sort of interesting. We may want to go with that. That returns a builder with false positive rate. I'm guessing the next method you have to call on that is expected items. And we should look briefly at the Erlang implementation and see what sorts of parameters it uses on its Bloom filters. The other thing we could do is say with num bits and number of hashes, right? So let's look at this builder with false positive rate. Okay, immutable false positive rate. So this gives us an option of a seed, so we can pick a seed. I don't think we'll want that. We can pick a hasher. We can pick expected number of items, or we can give the set of items directly. So this is just like, you know, it's a known size iterator, and all of the items in it have to impl hash. Luckily, string impls hash already, so we don't have to bother with that. Slices of U8 or vec U8 do as well. Okay, and then they have some things where you can set the block size. Okay. So we can either choose the false positive rate, or we could choose number of bits, which gives us a Bloom filter with bits. And again, you have seed and hasher, you can set the block size. And this one has hashes, so using the provided number of hashes to return an empty Bloom filter. And I think this implements default, does it not? No. Okay. We're going to go ahead and add this crate, and then we'll jump over to the Erlang and see what sorts of parameters they use on their Bloom filters. Okay, so that's interesting. Interesting that it pulls in WASM bind gen. I wonder if we can turn that off. Let's look at rand is optional. Oh, that's probably coming from rand. Or get random, which has some bindings to. Here, let's look at the repository and look at the features in their cargo toml. Now they do have an implementation of Serde, but I want to see if we can avoid adding Serde to this project. Because I think what we can do is use. Hi Isaac, good to see you. I suspect you're in Europe, right? We're finally no longer on daylight savings time, so it's a bit later for you. Okay, so their implementation of Bloom filter has this bitvec, and then it has some fields in here. So we might be able to, if we look real quick back at the, nope, not there. There is a, there was a way to extract the bitvec. And if we know the other parameters, we can make our own serialization of this, and we don't have to do Serde. There's a question of, does the hasher state need to go in there? And I'm not sure about that, because it is, once they're written, they're immutable, right? We only need to reconstruct the state. We don't need to be able to add new things to it when we're reading a file. So right, so we can give it a vec right, and those are the bits. Yeah, I suppose that might work when we reconstitute this. So if we can get the bit back out, it does depend, notice here, on the block size. So, and I say that that's a const generic I mentioned earlier. So we'll use probably 512, which is their default. But let's go down. So here's where you can insert. You can check if it contains. We'll be using that. You can get the number of hashes, number of blocks. Okay, so we can get as slice, which will give us U64s. So that gives us the contents of the filter, right? And then right. Okay, so they're just saying here in this doc test that if you create a vec that has 8 U64s in it, and then you create a Bloom filter from that vec with this, a static number of hashes, then and then you say, give me this Bloom filter as a slice of U64s, you get back the same data. That's just all this doc test is saying. Okay. Okay, and this is just saying you can add a bunch of things to this filter by iterating over them and inserting them. Okay, and equality. All right. So I think that we're in a pretty good spot to start using this. And let's just go back to the docs page. I think that, yeah. So I added it to our crate. And real quick, let's look back over here because there's this, and I still don't have ELP. I think I'm going to have to like rewrite my Z config in order for this thing to work. Or maybe I need to set up Erlang in a different way. Okay. So if we go down to where it's creating a scalable Bloom filter. So fixed capacity Bloom filters. Okay, so they're saying if you're just giving a capacity, the default is going to be n and then like 1 in 1,000, right? And then okay, so then there's something about here we're going to create it with a certain size, and then there's a check here. It looks like n has to be greater than 4 over the false positive rate. So, and that's probably because there's 4 hashes. We'll see. Okay, and then you could do. That's interesting. It has number n is float. This doesn't say is integer, which is interesting to me. Anyway, okay. So this is for the case where n is greater than, so it's bigger than 4 over the error rate. Then it's saying use a size based. This one's saying otherwise use a bits based. So like let's say you had your error rate is 1 in 1,000 and the size of your filter is smaller than 4,000. Then it'll use bits. Okay, and then it's doing some computation here. And this is the pure Erlang one, I think. There was an option in the configuration where you could pick a C implementation of this. but this is good to understand a bit. So right. So I think where we want to look for this is in the writer. So let's look for bloom filters. Okay, so it's got eBloom or SBloom. eBloom I think is the C one. And let's just jump down. Okay, so it's creating a new one, and it's using size. So we know the size is okay. So this is bits. I'm guessing 2048 bits. No, that's the default. And there might be options. So let's look at something that will write, like nursery or merger. And let's look for writer. Okay, so its merge has a size parameter, so it is passing size. And I think that's the, if we look for where this is called, okay, so let's find Hanoi. We need to find in project HanoiDB merger start. Okay, right. So this is saying for a merger, this is like, do the bit shifting to get a power of 2 of the level size plus 1. So this is number of entries, right? Yeah, that's a good question, Isaac. Thank you. Is your goal to be bit compatible with original Erlang code, or will your implementation have its own Bloom filter flavor? Is file format flexible enough to deal with this? We will have to address that. Unfortunately, there are probably too many potential incompatibilities with the Erlang version that we're going to bump the version. We're going to bump the magic number on the file in this stream. Because before we could say, hey, the Bloom filter is empty. Maybe you can read it from the Erlang code. No guarantee necessarily. But on this one, we're going to go with our own this crate that is pulled in, and it is not necessarily compatible with the Erlang Bloom filters. So we can't make that assumption. We're going to bump the version number in the file and just say this is a new format. It'll essentially be the same, but it's just that, like, that part I didn't want to deal with. so we'll have a new file format, and that's fine. Like, our goal here is not to be necessarily interoperable. It's to go, like, let's understand this Erlang code and what it's doing and the choices that it made, and see if we can re-implement it. So yeah, that's a great question. Okay, so they're using number of entries, basically. I think that gives us the answer that we want. Let's go back here. It was in writer, and see how they're creating the Bloom filter again. So yeah, they're just calling Bloom new size, which is the util Bloom new. Okay, and here they're for the SBloom, they're actually using a false positive rate of 1 in 100, which is pretty small. Like, that's going to be pretty frequent. The trade-off there, of course, is space, right? If you want a smaller false positive rate, you need it to be sparser, so you need more space. I think that gives us what we need. We can start with this, and maybe what we'll do is we will, probably not today, but at a later time, we'll potentially set that false positive rate, and then see what happens. Do we under load? Do we save enough IOPS? Or how much additional space is needed for another order of magnitude less false positive rate, right? That's a good thing to measure. It's at a later point. Okay. So most of what we're going to be doing here is we're going to look in format where our tree is defined, and I almost want to rename this module, but we can refactor that at a later time. And we need to work in writer today. So we already have those open, and we will need to initialize the writer with the level information or number of keys. So we can probably do level, and yep. So let's look in format, and we want to, first of all, we're going to change the magic. So let's do that. We're going to bump this version. In the writer, we're going to bump this version. Now, one thing that I may do is, let's pull that up into a constant. We're going to do that. And then we'll call this magic. Okay. And then we're going to move that over here as well. So we're going to write create format magic as bytes. And we can probably let's import that. Yeah. Cool. Okay, so now we have a new format. Let's really quickly, before we add the bloom filters, make sure that, and I'm going to remove this test.HanoiDB anyway. We have not been working with it in quite a while. Let's run our tests and make sure that they still pass. I imagine that we actually broke something, so we'll find out. Yep. We have one failure. Okay, and that is literally the magic. Okay, so if we go to writer 346, isn't that nice? It's nice to have tests backing you up as your wingman. Okay, so I'm manually bumping that, and I'm not going to reference the constant. I think that it's nice if this fails when we change it. Right, it would have been cool to have some golden references test, but being bit compatible would impose some limitations, so it's understandable for the version. Yeah, and I completely agree with that. The other thing is, I think that in the original Erlang, hey Matanya, everybody say hi to my coworker, my new coworker. To your point, Isaac, about golden references, I think that the original code sets the bloom filter type by configuration and not by reading any metadata in the file. So like when you load that file, it's expecting either the pure Erlang scalable bloom filters implementation, which is by Carlos Baccaro, by the way, originally, or the C version, which I don't know how that one works. I haven't looked into it closely. And if you try to read one or the other, you're probably going to just fail to load it, which means it'll either like fail to load that file completely, or you'll load it, but your bloom filter will be empty because it doesn't know how to read it. And we're in that latter situation right now, right? Because we just kind of ignore the bloom filter, but we want to add that. So yeah, anyway, excellent point, Isaac. And I think that I feel comfortable bumping the version. So let's run that test again. Yes, the nursery tests take a long time. and the integration tests. Thanks for coming to the stream, Matanya. I don't know if you caught up on any of my old ones, but we are working in database land. We're writing a database engine. It's an ordered key value store based on LSM trees. So, okay. So let's look at that. The diff. Don't diff cargo lock. I don't care. Okay, so... All right. So I'm going to add source for this, and we're going to say, we're going to go ahead and commit that. Bump file version magic in preparation of adding bloom filters. Okay. All right. So, excuse me. So now we're going to figure out how to read the bloom filter, because we need to, let's see. I think this is in the trailer. The question in my mind is, should we load this trailer when we try to load the file? And I suspect that we should. Note that when we do the root block, we get the trailer. We read the trailer to find the root position, so the first block, or rather the root of the tree. But I think we need to read this on load. And we're going to change this, right? Because we don't want to construct this data structure every time we load the file, or every time we go to seek to a different block in the file. The whole point here is that we should do in get entry, right, this to do, right? Read the bloom filter and bail early if it's not in the file. All right, yeah, see you tomorrow, Matanya. Enjoy your chores. Yeah, so I think that we're going to need a refactor here, which is we try to read the trailer at startup. And I think that that's... We can turn this into a private function. And have it pass the file. Okay. Yeah, because I think that we want to get this on startup. So, and then we can use the trailer. We're going to make it into a class or type level function and pass file, right? And then we'll pretend that this is there. Okay. And then here we can just do self trailer. And we're going to have to make sure that that can be cloned. Right? Right, so trailer doesn't implement clone yet. That's trivially clonable, so no copy though. Easy enough. Oops. Okay, so let's go back in here. And this needs to be, we're going to take file is a file. And I think we can do just mute like that and get rid of that. Yeah, so this is not, why is it saying use a, okay, it needs to not be pub, first of all. Why is it complaining? This function doesn't have a self parameter. It doesn't need one. We've got a conflict. Okay, so let's rename this to read trailer. Okay, we're fine there. Now here, this we need to say read trailer. Okay. Function doesn't have a self parameter. It doesn't need one. This is kind of a, what? Here. Let's see. So where is this length? Okay, so we need to pass len. That's the problem here. We need to pass len. And this will take len is a U64. And then we'll remove it here. Okay, so that's just about expected file length. That's why I was complaining. It's like, you don't have self. I'm like, I don't need self. Okay, so this is the part of the code that we want to change, right? And it'll be, we're just going to go ahead and put this up at the top. We need to think about how we want to serialize this. Hello, Sammy Fawcett. Welcome to the stream. Okay, we want to think about how we should serialize this. And I think that doing it manually is fine. It'll be a little bit ugly, but we can do that without Saturday. Because I don't want to pull in all of Saturday and then like a format. I think that that's kind of a pain. Now we could potentially look at archive. I believe that's, yeah, zero copy deserialization. And just give it tuple, like a tuple of all the things that we care about. And though this may also be too much. So let's go back here, and specifically I think we had, let's open the repository again in a new tab. I probably need to get dark mode on GitHub. So remember, the contents of are the bits. So that's the slice of U64s, basically. We could look at the implementation of that. That might be interesting. I don't know if we need any of the rest of this. I think we just need to statically set what block size we want. And then, read a vec of U64s. Which is going to be interesting in itself, reading that vec of U64s. And then we call this constructor. This is for the read side, not for the write side. Remember. So, okay. Wow, Sammy, Bloom filter. You missed the earlier explanation, and I think I closed the tab. I did. So a Bloom filter is a set as a bit vector that lets you quickly determine whether a given key or a given item might be in the set. It gives you false positives based on a rate that you choose, but it never gives you false negatives. So the reason we're using this, to be brief, and I'm sorry for repeating myself for the people who've been on the stream since the beginning, the reason we're using this is to cut down on IOPS. So if a key does not exist in a file, we can know immediately that we don't need to go look for it there. So you turn an O log n operation based on the B tree into an O1 operation for negatives. For false positives, you still may go into the file and not find the key. For positives, you're going to do that work anyway to find the key. So the trade-off there is pretty nice, especially if you have bigger and bigger sets. So that is what a Bloom filter for. We're using it in the read path of our database. Okay, so we need to first of all change the trailer. And what we might do is say, move this into the trailer as a constructor. I think that'll be a good way to yeah, we're gonna have to change how this works, which is fine. Right, so what we can do here is actually, I like this idea. So here we'll say reading the trailer is like outside the scope of the actual trailer, but we can give it the vec u8. So let's go ahead and change this. And we've already validated it's at the right size, right? So we just do that instead. And then we can put the logic down here in the constructor for trailer. Let's really quickly, before I make that change final, let's run the tests again. Yeah, okay, so we've got oh, right. So we have to read trailer. This is actually, we just need to return this. We don't need to wrap with OK. Okay, so let's go to that definition and run our tests. Now it's saying that length is never used because we're reading the trailer up front. Yeah. Oh no, it's fine, Sammy. Don't worry about interrupting. I like my streams to be educational, so please do not feel sheepish about asking questions, even if I've answered it before. Okay, so now rather than this being yeah, it's interesting. We actually don't really even need this except for when serializing. So we can probably get rid of that, because we're, rather than storing the vec of U8s here, we're going to create the fast bloom data structure. We might need to have some way to say this is a, we didn't actually read this. Like we had corruption when reading it. Although I think my intuition there is saying just bail. There's a trade-off of reading an empty file. I think if the length of this serialized bloom filter is 0, we know we have an empty file, and we can just say, yeah, just create one from scratch of the size that we want. If it's not 0 length, then we need to try to read it, and we should fail to read it if it's corrupted. See, okay. So Sammy, this is some context you need. The question is, what's the use case of a bloom filter when a regular hash table exists? We're not dealing with in-memory hash tables. We're dealing with on-disk B trees. So the cost of looking up a single key in this B tree is potentially, log 2 of the number of keys in the file. So that's not exactly right, because it's the nodes of the tree are based on size and not number of keys. Rather, the fan out is based on content size, so like how much data. So you could have potentially a file with 1 key in it and 1 level, or you could have a file with 3 keys and 2 levels, because those keys are, the contents of the value for those keys is huge. So they're trade-offs in that space. But basically, we want to avoid going to disk if we can. That's why we're using a bloom filter. Okay. So again, the concept of this is the trade-off of looking in the bloom, like hashing the key and looking in the bloom filter to see if it exists. That cost is way smaller than the seeks it'll take to actually fetch it from disk and find that it's not there. So that's the trade-off we're working with. Okay, so we don't actually need to construct this other than to say this needs to fit. So I think that we can remove this from the struct. And then we'll just, underscore that. We just want to check that is not too big, right? So let's say raw bloom. We're going to call that raw bloom because we're going to construct one after this step. Now, what we could say is we could simplify this. We could say if raw bloom len this I think is a simpler way to say it. I'm going to say return error bloom filter too large. Because since we're not storing this, we don't need to try to convert it. We just need to make sure that the length of this is less. It's smaller than 4 bytes. No, that's right. It can be represented in 4 bytes. Right. Okay. So now we need to convert the Bloom filter. And this is where it's going to get interesting. So the other thing we can do is say if raw bloom.len, or we could say is empty. Yeah, say if it's empty, then we can return, okay, we know that there's nothing in this file. This is the other case I was thinking about. Okay, so Bloom filter is too big. For our file format. This is that case. And here's the case where we know that the file is empty, so the Bloom filter was written as 0 length. Now this is not necessarily going to be the case after we've switched to using this Bloom filter crate. It might just be, the default bit vector size full of zeros. So yeah, that's something to think about. Okay, so here let's go ahead and use the crate Bloom filter, because now we're going to. Here, I need to jump down to the trailer again. Now we're going to change this to be a Bloom filter. And we need to tell, I think I'm going to use their default block size of 512. Now I think, let's see. Yes, that's the default. Yeah. That's the default, so we'll leave that on there. And here's where we can do with false positive rate. We'll use the thing that was there. And what does that return? That returns a builder with false positive rate. And I think we just say expected items. And here, because we don't know what level the file is at, let's use the default smallest level of 1024. And that returns a Bloom filter. So we're good there. And then we do root position. And here we say return. Okay, so we're just bailing out early and saying here's an empty Bloom filter because the contents on disk were empty. Okay, now we need to transmute this into a vec of U64s. So we potentially have another error condition here, which is this not a power of 8, right? Or multiple of 8. So let's make an error for that. Let's go to this error definition. We're going to add Bloom filter to large. Let's add a new error here, which is Bloom filter is bloom filter incorrect width. What did I say? That's not a great error. What I'm trying to say here is it needs to be multiples of 8 bytes. Um, um, there we go. We'll say misaligned. It's not really alignment in the sense of RAM, but this is we'll say incorrect length or incorrect size. That's probably good. Okay. So so if we know that it's be composed of U64s, then the length mod 8 should be 0, right? Okay. Right, so in order to be complete, it has to have that. Okay, and then we want to reinterpret this vec of U8s as vec of U64s. So we're going to have to dig in the docs for that real quick. And I think we can probably do something like from bytes. Right. Let's see what they say. Okay. So read a U64, and this is slicing, right? We could potentially, right, so this is, we have to use fallible conversion APIs. But what we could do is on, let's see, on slice, there is a way to get chunks. Ah, that's nightly. Boo! Array chunks is nightly. Boo! Chunks exact? Ah, okay. So this gives us an iterator. And we want, okay, so we're trying to get chunks. We're going to map them into U64s, and then we're going to collect them, right? Yeah, chunks exact. Okay. There, you know, honestly, okay, thank you for laughing. There are times that I look at the docs and I'm like, why the heck is this nightly and not stable yet? I've been working in this for 3 years plus, and it hasn't been stable that entire time. But it's just like the open source, you know, people use their own time to do things often. Okay, so then we're going to collect the contents as a vec U64. Okay, so we're going to take let bits, we'll say bit vector, because that's what it's going to be in the bloom filter. So we're going to take the raw bloom filter, chunks exact. Wait, what's the difference here? Right, so chunks exact does not divide by the length of the slice. Yeah, well, we've already validated that it has the correct number. So we're going to take 8 bytes, and this is bytes, and we're going to say U64 from BE bytes. The question here is, what does this give? It gives a slice of U8. And we can say try into question mark. And then we're going to collect. So this is going to give should be giving us a vec of results, but we want a result of vec of U64. Okay. And then we can see if we can do question mark. I don't think that that's going to work. Right, so what is our map doing here? Right. What did I do wrong? Here, let's remove the turbofish here. So bytes is a slice of U8s. Oh, okay. We did this elsewhere and it's actually in this file, so I can just do that try into. Oh, right. Okay. So I know what we need to do. We need to do, rather than trying to pull that out, we need to do OK. That'll give us the signature that we want. Okay, so and this already works because we have on our error where is it? Slice conversion. So this try from slice error on standard array. So an internal buffer conversion error. This is just saying this is a case we have to cover in that if you give it a slice of the wrong size, it's not going to be able to convert that into an array of the desired size. It's just sort of a weird aspect of this. There are crates that kind of handle this problem. Okay. Actually, so hold on. I put the question mark at the end there and it probably figured out what I wanted. Let's see. That says the never type. Okay. Okay, so we're going to collect that into a result of vec of U64. And we don't care what the error type is. And what's wrong here? Oh, okay, this is the thing. We have a type alias in here. So this is collecting to a result of our own type, which is our error type. Yeah, that's correct. So now we have this. We can construct the Bloom filter from that. We can say that's Bloom filter from vec and give it bit vector. Let's rename that. We'll use the name that they do. Bitvec. Okay. So we probably need to be tracking in here. let's see again what that returns. So we've got, this returns a builder with bits. And what did we do up above? We returned a builder with false positive rate. So let's see what we can call on here. And I think the it may not be sufficient to just read the flat bit vector. We might need more information about how it was constructed. Either the number of items, which would be a power of the level, right? Or one of the other things. Right, so okay. Sorry we're digging into the code of the Bloom filter here. I think it's kind of important to understand this if we want to serialize it correctly without using serde, which may be too tall of an order. I think what I'd like to know is how these individual fields in here are computed when you're constructing it. So like how many target hashes are needed based on some other factor, you know, or num hashes or number of rounds. So let's go to this one. That's a test. Interestingly, the seed is not set in that constructor. Let's look in the builder. Okay, so that's a test. So here's the builder file, which is where those things are. Okay, builder with bits. Okay, then you can seed it, and that returns self. So that doesn't finalize it. What we want is, so the ones that consume it, the ones that take self and return something else. So like this one returns Bloom filter. That's private. This one takes expected items and returns Bloom filter. Okay, so num blocks items per block, num hashes. Okay, so they're kind of computing how many hashes should be used based on the expected items. And we were constructing with a false positive rate. Is there a way to get the false positive rate and then say, here's your stuff. Here's your bit vector. It doesn't look like it. Okay, so what they do with the false positive rate is say, how many bits? Like, Okay. Let's look at this function because we might be able to reverse engineer, well, how big is this? And if we have a static false positive rate, we can say, well, how big do I think it is? And then call this expected items thing on the other one. So where's this optimal size? Okay. I don't know that that's reversible. Oof. Okay, items count, false positive. Yeah. This doesn't really feel reversible. So the result is bigger than 512 or you have 512. So like, oof. And there's some, there's some rounding there that like is using ceiling and max. So I don't know that that we can reverse this items count and false positive rate from this. Let's copy this function and see if we can reverse it just for fun, and then we'll move on, because I think that we probably need to. The long-term answer is I think we need to get more information from the Bloom filter to serialize, and then we can deserialize that information and repopulate it. So that's probably what we will end up doing. Okay, so let's kind of reverse this. So if we have 512, yeah, let's make a new one. Reverse optimal size. So we know what the output of this is. So size is a U size. And then we know what the false positive rate is, F64. So we're going to try to get an F64 out of that. Okay, so we're going to do the same there, because if it's bigger, we know it's 512. Or I'm sorry, if it's bigger than 512, we use that. Or do we do min there? Max is not exactly reversible. But we're just trying to get an estimate, right? Thanks, Sammy. Have a good weekend. Hope to see you next time. Okay, so we've got we don't need to do this because we know that the output of this is going to be a minimum of 512, right? That's what that means. So this could be bigger if the result of this computation is smaller than 512 when we're trying to reverse it. So we're going to be a little bit lossy on this computation. Okay, and we can't account for the ceiling function here. So let's just start computing this. We're going to need this log2 too. And I'm assuming in the original code, let's look. Yeah. Let's import that. Okay, so let's assume that the ceiling, we're just gonna like actively refactor this as we go. So we're not worried about truncation, and we're not worried about ceiling. So what we need is we're gonna let size as f64. So we're gonna convert that usize to an f64 so that we can do this stuff. All right, so now we just have to worry about algebra, right? Right, so let's start dividing. So we're going to have, we need to multiply by this factor. Or multiply by that, because we divided by it originally, right? So we factor that out. We need to divide by f64 pow of hold on. We want the natural inverse of the logarithm is the exponentiation, right? So x, that gives a natural logarithm, doesn't it? Yes. And since here fpp no, I'm thinking about this wrong. We want to divide by f64 of the natural logarithm of p of that, right? So we know what this is. It's going to be constant. Okay. And then we'll divide by 8. So I pulled off that factor. Now we have 8 times items count. And okay, items count estimate, we're going to call that, given a bit size and a false positive rate. Okay, I think that gets us what we want. And then I think we don't want to return an f64. Let's look at how let's look at how they use it. So who's calling optimal size? It's in this file, expected items. Okay, so they're converting that to an f64, probably to simplify. Yeah. And that gives them the number of bits. So, interestingly, I think that let's go to this. Right. Okay, so they're saying this is the number of bits. So what we can do is we can look at the length. We can look at the length of this Bloom filter that we have serialized. And let's go ahead and say we're going to round up as they did, right? And then we're going to convert it to usize. So what's wrong here? Oh, I need another paren. Is that right? Let's inline that. into one expression. Yeah, I think we can simplify this. FBP logarithm, like so. Okay, so that's around that. Then we have that around that. Expected semicolon. Expected expression. What's going on, folks? Let's break this down. There we go. Okay. Algebra, it's useful. Okay. So, so we can know, or we can estimate from this, we're going to say expected items. Use items count estimate. And here, the size, remember is the number of bits, right? So this is expected number of items. So we have the number of bits. So what we'll do is we'll say this is raw bloom dot length times 8, and we're going to use the same false positive rate, which means I should probably get a a constant for that. Okay, so we've got from vec, which gives the builder with the default number of bits, or the block size is 512, and then we can say expected items is expected items. And there we go. Okay, did everybody follow what we did there? We're kind of reverse engineering the number of bits it takes to store a Bloom filter in this library that has a false positive rate of 1 in 100. That is really big. Sorry, and then we are using the contents of the Bloom filter we loaded off of disk, the serialized one, to go into to construct this. So now the trailer, we need to be able to encode as well. So now this is not going to work. So what we're going to do is we're going to say self bloom as slice. So that gives us a slice of U64s. And then we're going to map that with, this is a U64. So we'll just say it's a number as, I'm sorry, we need as slice iter map as BE bytes, because we're just, for Erlang reasons, we are yeah, we'll use flat map. Not flat map map, flat map. Okay. So we also need to know how long this is. So we need to go, let's say bloom is this. We'll call it raw bloom. And we need to do collect. So this should make a, well, we'll find out. And then we're going to do raw bloom dot length. Try into U32. Yeah, I think we need to do an infallible conversion here. Okay. Can we do 2? Yeah. Okay. So that returns. No, this returns an array of U8s, and then we're flattening that, and then we'll collect it. So this should come out as a vec of U8s. Let's see if the compiler can infer that. Well, it's not complaining. um, so as slice on the bloom filter returns a slice of U64s, right? Do we even need this iter? Yes, we do. Can we do into iter? They're copy, so it still borrows. Okay, doesn't matter. Iter into iter. Okay, so we are explicitly telling it it's vec of U8. We could potentially do like a panic here or an assert. I don't really like to panic in this scenario, and I would rather go. God, it's it's a problem if this length is bigger than U32. But like your bloom filter is always going to be like significantly smaller than the amount of data you're storing on disk. So if it reaches the, what is it, like 4 gigs, we got a problem. Okay. I need to find where this is used. Right. So the writer. Okay. So the writer constructs a trailer. I think we'll need something that we need to distinguish these two things. Right. Um, let's go to where this is. Okay. So this is closing it. And I think that we want a, yeah, so we're going to need to get to that. I think that we want a constructor that takes the bloom filter. Because we will have created it for this writer at the beginning. So, okay, we've got about 20 minutes left. Let's look at format. And I think this is fairly clear what we want to do. Let's run our tests. I suspect that some of them are just going to break. Yeah, empty file broke. And I think that we need to make sure that we handle that correctly. That's interesting. Oh. 1306. It's in writer. It failed in writer 345. Okay. So interestingly, I think the issue here is we are writing the trailer with a big bloom filter. So we need to handle the write side and the read side differently. And I think that this is like read with the intention of using this trailer. But what we want is like a with bloom filter. And maybe what we can do here is and this is going to be a bloom filter and root position U64, and this is going to just be self. Let's be infallible. And I think that we want to do here, convert this to that. Not that it's strictly necessary in this case, but it's important to be clear that this is the read side and this is the write side. And the main thing with this constructor is just to make sure that we can construct it outside this module where it's defined. And we were not doing that. Okay, so this test is going to be invalid. I can tell you that right now. But we're going to have to change quite a few things. And maybe we can go a little bit over today, beyond the usual 3:30. Okay. So let's go up. Okay, so we're gonna import this. Use fast bloom filter. Okay, and then for the constructor, we need to pass either the level or the expected size. So I like the idea of expected num items, right? So then we'll do let bloom is bloom filter with false positive rate. Remember, we're using that. Doesn't make sense, but, and then we'll use expected items. Yep. And then we can add bloom in here. I think I put it under blocks. Did I not? Yeah, it was under blocks. Okay, so now we need to do two things. When we append to block, so we add an item, we need to add it to the bloom filter. And we're going to insert entry.key. Right? However, we don't want to add internal entries, right? because they'll just, let's see, if entry is key value. Thank you, Derive More. So if it's key value entry, we want to, we want to add it to the Bloom filter. If it's not, if it's a, we actually want, we only care about deleted, or we only care about not adding internal entries. So entries of the internal nodes of the tree. If it's a tombstone, we still want to read it, right? To know that it's deleted and that, know that it's deleted and then it overrides anything that may be in deeper levels, or adjacent files that are older, or if it's an actual key. Okay, so if it's not an internal node, then we add it to the Bloom filter. And here we're going to say trailer with Bloom filter, and we're going to say and I think that it's safe because this is consuming. Oh, there's no try on that. Okay, so then we encode the trailer, right? Now this test is still going to fail. And we haven't updated the places we call this. So let's find all references. That's probably a test. That looks like a test, yeah. Now we could make, nope. Yeah, let's rename this with expected size, right? Num items. Make it a bit verbose. It's fine. And then for new, we'll take name, and we'll do that. And we'll say result. This is also result self. And we'll say self and we'll pass name, and then we'll say, the bottom level. That's just so we can make our tests a bit easier. But when we're actually writing files in the other places, we'll know what this number is based on the level, right? Okay. So let's go to find the places that call this. Okay, and we don't care about the ones in this file. Let's look in the merger. So the merger, we know what the level is. So here we're going to say with expected num items, and we're going to say one bit shift left level +1. I think we had a function for this or something, but that's okay. So we know that level, so if it's level 10, we want to merge into level 11. Level 11 is going to have 2 times as many keys in it. So that's what we're doing here. A little bit shifting math. And where else was it? So we had it in merger. This is a test, so it's fine to leave it there. Those are all tests. Those are all tests. Okay, so we go to the nursery, and it's going to write what the min level is, right? Now we could move that computation into the writer. but this is going to be with expected num items, right? Okay. And we actually have min level size there, so we don't need to compute that again. Min level size. All right, let's see where else it's done. Is this a test? It is not. It's the recovery. So do we even know? Target level. We've got target level in there. Yep. Okay. So so now we are constructing a properly sized Bloom filter for the expected level. Now what I would expect to see now is the empty file test is still going to fail. We can probably fix it. But the other tests should still pass. It's a good sign that the writer test round trip succeeded. Okay, so that's interesting. 1280 is suspicious. Okay, so I think I'm just going to fix this. This test. What we can do, I'm sorry, I'm looking in the nursery, wrong file. We'll fix that warning in a minute. We're going to jump down to tests, empty file. I think what we should do here is we're going to make a Bloom filter. So this is the Bloom filter. We're going to say let bloom len is going to be bloom as slice length times 8, right? So we're going to say we don't know what that is, right? It's whatever this is. But we're just adding it in there, so we know it's 26 plus bloom len. And then so here's the padding. We don't, do we even need to assert this? I honestly think that we don't. We'll skip over the Bloom filter. And then we're going to go and here we're going to say rather than zeros, because the bloom len is no longer 0, we're going to say bloom len as BE bytes. I'm sorry, that's as U32 as BE bytes. Or is it 2 BE bytes? Sorry. And then we have to add that to here. Okay, I think at this point we will be able to pass this test. And then our last bit will be fun, which is we add it to the read path. Okay, so now it's just saying that new is never used. And look, our empty file thing passed. Okay, this does make our files significantly bigger. Like 1K for an empty file is a lot. But it's working. Yeah, so I think that we can do what we can potentially do is move this implementation down into the test module. If you didn't know that you can do this, you can, because I don't think that we're using new from anywhere else. We're just using it as a shortcut here. You can, in a child module, you can implement any method on a parent type, a type from a parent module. Sometimes this is nice if you want to segregate different aspects of your API for something, if it's a pretty wide API. Okay, so let's that should remove that warning. Let's see what the existing warnings are. Length file is never read, or length field. Okay, well, let's remove it. And then we don't care, because the length is really about jumping to read the trailer. And then we don't need it here, right? Anywhere else? No problems. Cool. Okay, so that was a lot. We're just going to add everything new, and let's look at the diff really quick. Okay, skip over cargo stuff. Okay, so we got fast bloom. Made trailer clonable, and we read it at startup rather than trying to yeah. Okay, and then we did all the stuff for deserializing the bloom filter. Now we probably should do, I mean, because this is messy, right? We made a lot of assumptions in here that may not hold, especially this reverse engineering of the size of the bloom filter, or the expected items. Now, a different approach we could take is okay, well, there's two different approaches we could take. We could take the Saturday approach, which we may try next time, see if it makes it any bigger, honestly. Or we can take the approach of feeding in based on the level what the expected number of items is. That would be really consistent, I think. But then when you open this file, you need to be able to tell it what level you're in. And that's possibly something we could do when we're doing like open my files in the level struct. So we might possibly do that. And we need to get rid of that commented out code. And we'll make a What file was that in? That was in format. We'll make a note on that estimate, item count estimate. Reverses the expected number of items from the size of the bit vector. Reverse engineers, and then we're going to say C fast bloom optimal size function for reference. Okay. And I actually maybe have a problem here. Where are we calling this? Calling it from here. This is number of bytes. Right? How are they using it? Let's make sure that we didn't mess that up. They're doing the number of bits. So we need to add another 8 there. That's the number of bits, not the number of bytes. So these are 64s, right? Let's do. Oh wait, I'm sorry. That original was correct because the raw bloom is vec u8. The bit vec is vec u64. Okay, I was wrong. That is still correct. Okay. Let's look at the diff again. Let's look at lazy git this time. Okay. So we no longer need the length. Got the trailer. We can inline that. This is self.trailer root position. Okay. And we're going over a little bit. Maybe we won't get the read side in there. I just want to make sure that we have a clean commit to do. Because even if we're not using the bloom filter, it's still safe to write it to the disk. We hope. Okay. Here we go. Let's look at this one more time. So error is fine. Format. That's all good. Okay, and now it's actually a bloom filter. Yay! All right, and then we've updated that. And then we're serializing it. Okay. Let's look at merger. We just use the new constructor there. The newly written constructor. Same in nursery. And then in writer, we actually have the bloom filter field. And we have this with expected num items. And it creates the bloom filter and puts it in the struct. And then when we add an entry, if it's not a if it's a key value entry or a deleted entry, then we insert it into the bloom filter. We construct the trailer directly from the bloom filter this time, and at the end of this, instead of from the vec, and then we moved our new down into here to make it easier, and then we are making the default stuff there. Okay. All right. I think that's a good place to make a commit. This is session 15. Read and write bloom filters from the tree file. I'm going to say read and write bloom filters without guarding the read path. Now, it's very possible that we can just add this in like 5 minutes. So let's see if we can do that. So the function that we care about is get entry, and this is where our to do is. So here we can go the question is, what does this take? Okay, it's a reference to something impl hash and sized. If we know it's not in there, so this is where the no false negatives works in our favor. If we know it's not in the bloom filter that is contained in the trailer struct, then we just return none. So we know it's not in this file. Like I said, 5 minutes. Except it took less than that. It took 2 minutes. Okay, so honestly, this is a very... unless we see tests failing. We see tests failing. Okay, so we've got some work to do there. I think that's a good place to stop, though. Right, this one says it is some. So we have an issue where we're probably not. We got that truncation problem we had before, I think. Or is that the word key? Yeah, so either these are not hashing the same way, or when we deserialize, we don't have enough information. That's probably most likely the problem, is that we need to go and be a bit more rigorous about this and not go, oh, just give me the bit vector and we'll pretend that it's fine. So I think that's something that we need to fix for next time. So why don't I leave it there? So we'll say session 15, add bloom filter guard, but tests are failing on read, but tests are failing. Okay, I'm going to push all that to main, and we'll see you next week. We'll fix this bug. We'll figure out what we need to do to properly round trip the bloom filter. And we'll see if there's a way that we can potentially test that. I suspect we can. And then we will we'll keep going, adding things. Thank you for coming to the stream today, and we'll see you next week.